Okay, drop your attendance. So let us continue with the stability analysis. Okay, so what was the last topic of discussion? Do you remember? I think you may not remember. Okay, it's been a long time. So in the last class, we were discussing about uh, judging the stability using RH criteria, and we were also discussing about um, the difficulties encountered in RH criteria. And we examined difficulty one, and to overcome difficulty one, that is, if the first element of any row in a root array becomes 0, then that particular row will have at least one non-zero element, as an effect of which the elements of the next row becomes infinite, and due to which the method fails. So that was the difficulty. To come out of this difficulty, we proposed method one, and method one is substituting a positive integer epsilon in place of 0. After substituting the 0 element with epsilon, you can complete the remaining part of the truth table, and by applying limiting condition, that is limit epsilon tends to 0, you will be able to examine the sign change, and based on sign change, one could comment on system stability, right? So that was the previous class discussion. Okay, now the same difficulty can also be overcome using a different method. Let's call this as method 2. So method 1 was substituting epsilon in place of 0, and method 2 is something like, okay, so method 2 I'm going to talk about today. So in method 2, what you have to do is, as a first point, replace S with the new operator Z. So replace S with 1 by Z. And where are you going to replace, or where are you going to substitute? This S is equal to 1 by Z in f of S. So that is characteristic equation. All right. So what was our characteristic equation? So we had taken the characteristic equation as f of S is equal to S to the power 5 plus 2s to the power 4 plus 3s cube plus 6s squared 2s plus 1 is equal to 0. So this was our characteristic equation. All right. And what is that we are supposed to do in method 2? Replace S with 1 by Z. So let's do that. Or you can just say f of Z. Okay. Okay. You can just say 1 by Z, doesn't matter. So 1 by Z is equal to, let's do that. S is equal to 1 by Z. So 1 by Z to the power 5 plus 2 into Z to the power 4 plus 3 into Z cube plus 6 into 1 by Z squared plus 2 into 1 by Z plus 1 is equal to 0. Okay. So what you have done, you have converted polynomial of S into a polynomial of Z. Okay. In the next step, what you can do is you can take the LCM, because I don't want to have a series in which I have Z to the power minus 5, Z to the power minus 2, etc., etc. So what I can do is I can take LCM. Okay. So if I take LCM, what happens? 1 by Z is equal to, okay, the highest power is Z to the power 5. So you can take the LCM. So 1 plus 2Z plus 3z squared plus 6z cubed plus 2z to the power 4 plus z to the power 5 is equal to 0, right? This is what you get when you take LCM. And obviously, the denominator boils down to 0 because z5 gets multiplied with 0 and the denominator gets vanished. Okay. Now, by rearranging this term, basically you would get f of, let's say, z inverse is equal to, let us rearrange this equation in the descending power of z. So z5 plus 2z4 plus 6z cubed plus 3z squared 2z plus 1 is equal to 0. So this is our new equation, which is expressed in powers of z. Now, with respect to this z polynomial, okay, I would say this is z poly or z polynomial. Now, with respect to this z polynomial, you will have to create the roots array. Okay, the method remains the same. Instead of yes, you're supposed to take z. That's all. So z to the power 5, 4, 3, 2, 1, and 0. 0. So first two rows are constructed from the coefficient of z itself. So what do you get? You get, starting from the highest coefficient, the alternate powers of z are taken down. So 1, 6, and 2. 1, 6, 2. All right. And in the z to the power 4 row, missing terms are tabulated. 2, 3, and 1. All right. And then you continue with the completion of RH table. Remains the same. So this becomes 1 into 3, 2 into 6, 12, minus 3 divided by 2. So that gives 4.5. That gives 4.5. And the second one becomes 4 minus 1, that is 3 divided by 2. So this becomes 1.5. And this becomes 0. Okay. So similarly, you try finding out the elements of z square row. So it is 4.5 into 3 minus 2 into 1.5, that is 3 divided by 4.5. So the first element, you will get it as 2.33. Okay, I'll not write down the simplification of all this. I assume that you know how to find out these values. Okay, so if you have any doubts, you can ask me separately. Okay, ping me separately. Okay, I'll be able to tell you. And the next element becomes 1 if you cross check, and this becomes 0 because there are no coefficients. And later you have to find out the coefficient of z to the power 1, which can be done in this manner. 2.33 into 1.5 minus 4.5 divided by 2.33. So that will give you negative value, which is 0.43. And this is 0. And the coefficient of z to the power 0, you are supposed to get it as 1. Let us see, do we get it as 1? So this into this minus 0 divided by this. So you will get the coefficient as 1. That's it. So this is all about method 2. So quickly, let me just recall. So what did we do? We substituted s with 1 by z, and we created a new equation which is expressed in the powers of z. So basically, z polynomial we have created. And once you have the z polynomial, you construct the RH table in the conventional manner. and examine the stability by checking the signs of first column entry. So tell me whether the system is stable or unstable. Okay. So in the first column, as you can see that all the elements do not have the same sign. Hence, system is unstable. Unstable. Okay. So that's the first point, that is judging the stability. And second point is how many sign changes. How many sign changes in the first column. So 2 sign changes, right? Positive to negative, and then negative 0.43 to positive 1. So basically there are 2 sign changes. 2 sign changes. Okay. So what is that you are going to conclude? It's a 5th order equation. So out of 5 roots or poles, out of 5 roots, 2 roots are found in RHS of the S-plane, that is right half of the S-plane. Okay. So if 2 roots are found on RHS of the S-plane, the remaining 3 roots are on LHS of the S-plane. So that completes the stability analysis. Okay. I mean, with respect to this problem. Okay. Now, I want you to compare this result with method 1. Okay, are you getting consistent results? In method 1, that is substitution of epsilon in place of 0, had given the similar result, right? So even using method 1, you had found that the system was unstable. And you had also observed in method 1 that there were 2 sign changes. So number of sign change is equal to number of roots present in RHS of the S-plane. So in exam, the examiner will not compel you to go to method 1 or method 2. Whichever method is feasible for you, you can choose. All right. But in descriptive questions, something like, what are the difficulties encountered in RH criteria, then you will have to explain both the methods. All right. So this particular problem basically tells you how to handle difficulty 1. Okay, that is presence of 0 as the first element in any row of RH table. All right. So that's about difficulty 1 and how to overcome this particular difficulty. Okay. So we also have difficulty 2. So next up, what we have is difficulty 2. Difficulty 2. And this difficulty 2 is commonly called as row of zeros. It is also called as row of zeros. Now, what I will do is I'll not consider a problem to explain this difficulty. Okay, so what I will do, I'll just consider a generic case. Say, for example, let's say we have a RH table. RH table. Problems let us consider later. Z5, Z to the power 4, Z cube, Z square, Z1, Z0. Okay. So imagine that you have a 5th order system. Sorry, it should have been yes. So this Z is used only in method 2 to overcome difficulty 1. All right. So let's say I have a 5th order system in which, let's say I have the following coefficients, say some A, B, C here, and D, E, F here. All right, some coefficient A, B, C, D, E, F. And let's say when we try to find the coefficient of S to the power 3 rho assume that you get all the coefficient as zeros. So if you get all the coefficient in a particular row in RH table as row of zeros, okay, then it is called as difficulty 2 or row of zeros. So this is difficulty 2, which is also called as row of zeros. Okay. So this is difficulty. Next, what is the effect of this particular difficulty? What is the effect? If you have all the elements as 0, you will not be able to determine the elements of the remaining rows. So elements cannot be determined. So effect will be something like elements can be determined. Elements of the remaining rows cannot be determined. Okay, so this is the problem. So the method fails. Eventually, the method fails because you will not be able to find the remaining elements. So this is the difficulty. So how do we overcome this particular difficulty? Okay. So next you can write solution. Solution or method to overcome the difficulty. Method to overcome the difficulty. So what do we do? Okay. I hope you understood the difficulty. The difficulty is row of 0, due to which you will not be able to determine the elements of the remaining rows. All right. So this difficulty can also be called as the special case. Okay. So solution. Now, solution for overcoming this particular difficulty is to create an auxiliary equation A of S. Create an auxiliary equation A of S from the elements of a row which is sitting above the row of zeros. All right. So this is the solution. What is that you are supposed to do? Create an auxiliary equation A of S from the elements of a row which is sitting just above the row of zeros. Okay. So if you look at the root table, your row of 0 corresponds to s to the power 3 row. Correct? Your row of 0 corresponds to s to the power 3 row. So, but what is that you should do? You should create an auxiliary equation from the elements of a row which is sitting above row of 0. So what is that row? S to the power 4 row. So from this s to the power row coefficients, you are supposed to create an auxiliary equation. And let us call that auxiliary equation as A of S. Okay. So what do we have? The coefficients in the row which is above row of zeros. We have the first coefficient as D, and then E, and then F. Okay. So first you write down D, the coefficient value. Okay. And then you write down the powers of S. So what is the first power of S? Since it is s to the power 4 row, the first power of S is 4. Right? Plus the second coefficient. What is it? E. And what is the power of S? Can anyone tell me? you are dealing with alternate powers of s, right? If you start from s to the power 4, the next alternate power is 2. And then you have f, whose associated s term is s to the power 0. So s to the power 0 is nothing but 1. Okay. So this is my auxiliary equation. Okay. So mark this auxiliary equation. Okay. So this is my auxiliary equation. Done. After writing down the auxiliary equation, what you can do is you can differentiate auxiliary equation with respect to s. So differentiation means a dot of s, which is nothing but dA of s with respect to s. So differentiate. So when you differentiate, what is that you are going to get? 4du. 4d cube. Sorry, I'm sorry. 4d into s cube plus 2e into s. That's all. And this becomes 0 because you are differentiating the constant yeah. So this is your auxiliary equation. All right. Sorry, the differentiated equation. A dot of s. Now, by doing differentiation, what did you get? The highest power of s. By doing differentiation, the highest power of s has now become 3. I hope you got the idea now. Now, what was your row of zeros? S to the power 3. So, in place of all those 0 elements, what you can do is you can substitute a dot of s coefficients. That is 4d and 2d. So, substitute these in place of zeros. So substitute these coefficients in place of zeros. Okay. So let's do it. So S5, S4, S3, S2, S1, S0. Okay. So A, B, C, D, E, F. Right. So in your original roots table, what did you have? The first element as 0, followed by 0, and followed by 0. Now, in place of the 0, what is that you are supposed to substitute? These values you are supposed to substitute. And what are those values? 4d and 2e. Okay. So here I write substitute coefs of a dot of s equation. So that is the solution. Okay. Once you have the non-zero elements as the coefficient of s to the power 0, you will be able to determine this, 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 and this. And you can continue with the remaining part of the roots table. And then you can judge the stability by inspecting the first column entries. All right. Hope you understood this particular method. Right. So once you substitute these coefficients here, you will be able to complete the remaining rows of roots table, and later you can examine the stability by applying the criteria. All right. Fine. So far, so good. Everything looked normal, but there is a tiny problem over here. Okay, you can write on the subtopic as judging stability. Judging stability from method 2. Okay. So please follow the instructions carefully. Let's say you encountered a row of zeros, and as a solution, let's say you have created an auxiliary equation, and you substituted the coefficients of, let's say, the differentiated auxiliary equation. And after that, let's say you have completed the root table. Now, after completing the root table, if you find that all the elements in the first column, if you find that all the elements in the first column of RH table is having the same sign, okay. If you find that all the elements in the first column of RH table is having the same sign, the system can be judged as a stable one. This is very, very important. Quite often, even me when I was a student, like we have this common notion that, the moment when you get the first column entries having the same sign, we just jump to this particular conclusion. Okay, my first column entries have the same sign, so let me say the system is stable. That holds good if at all the system doesn't encounter the difficulty 2. Whenever the system suffers from difficulty 2, which is nothing but row of zeros, and if you, let's say, eventually if you get this particular condition, you cannot just say that the system is stable. Okay, so that's the reason I have written this particular statement. So system cannot be judged as a stable one. That's because row of zeros is an indication of, I'm not saying it is just an indication of something known as marginal stability. Something known as marginal stability. Whether it is marginally stable or not, I don't know, provided I find something. Okay, that is what eventually I am heading towards. All right. So row of zeros is an indication of marginal stability. That means to say, whenever you encounter a row of zeros, your system cannot be absolutely stable. Your system either unstable or marginally stable. So that is the stability judgment what you can give whenever you encounter row of zeros difficulty. So system can be either unstable or marginally stable. Marginally stable. There is no question of stable system, okay, which can be validated using experimental results, basically. Okay, these are not just statements. These statements have been proved by conducting experiments. Okay, so either you will get an unstable system or you will get a marginally stable system. Remember, please, print it in your mind that whenever you encounter difficulty 2, you cannot judge the system as absolutely stable system. Okay. Now the question is, how do we judge the marginal stability? Because instability is pretty easy to judge. How will you judge whether the system is stable or unstable? If, let's say, first column entry had sign change. So I've written here, if at all, first column entry in your Rx table had sign change, then you could outright you could say that system is unstable because there is sign change in the first column. This marginal stability comes into picture whenever you encounter this, that after getting row of zeros, if your first column entries have the same sign, then you cannot judge the system as a stable one. The system could be marginally stable or unstable, that we don't know. So that is what we are supposed to find. So next subheading, you can take it as judging the marginal stability of a system. Marginal stability. Marginal stability. Remember, this marginal stability is the subset of difficulty 2. All right. So I'm still under difficulty 2. I'm not done with that. All right. So let's see how to judge the marginal stability. To judge the marginal stability, what we have to do is you have to find roots of auxiliary equation. That is, equate A of S to 0. So what is that you are supposed to do? You are supposed to find the roots of the auxiliary equation. That is, equate A of S to 0. Now, these roots in control system are called as dominant roots. These roots in control system, it is called as dominant roots. Now, why dominant roots? These roots basically, these roots are nothing but few of the roots of f of s. I will not write what is f of s because it is known to you, right? F of s is your characteristic equation or main equation. So the dominant roots are nothing but some of the roots of the main characteristic equation. Now, having known the root nature of dominant roots, you can judge whether the system is marginally stable or unstable. Okay. So by finding the root nature of dominant roots, okay, so by finding the root nature of dominant root, the end result what you get is either marginally stable or unstable. Okay, what do you get? Either you will get an end result as a marginally stable system or an unstable system. Okay. So to find whether the system is marginally stable or unstable, what you have to do is you have to find the roots of the auxiliary equation. All right. Now, luckily, we know the system stability in terms of the pole zero plot, right? So having known the root location, one can say whether the system is stable or unstable. All right. Now, the dominant roots can be of the one of the 4 types. Okay, so dominant root falls in one of the 4 types. Okay, so you may get dominant roots which are having, okay, let me use the statement appropriately. So you may get dominant root something like let's say pair of real roots with opposite sign. Okay, let's say pair of real roots with opposite sign. Let's say we equate A of s equal to 0 and we get that s1, 2 as let's say plus a plus or minus a plus or minus a. So plus or minus a means you can draw the pole zero plot plus sigma minus sigma plus j omega minus j omega. This is your pole zero plot. Okay. And how are you going to place the root? One is having negative real part and one is having positive real part. This is minus a and this is plus. Okay. What will happen to the system response? Okay, let us consider the simplest response, that is the impulse response. When you have a pair of, when you have a single root on the RHS of the S-plane, basically your response becomes unbounded. So your output is unbounded. That's because the exponential function keeps on growing. You will get something like e to the power plus at term in your C of t expression. So this keeps on increasing as time approaches infinity. So if you get a pair of roots, real roots with opposite sign, what you can say? Your system is unstable. Right? Your system is unstable. Okay. So that is the first possibility of having dominant roots. That is pair of real roots with opposite sign. All right. The next possibility is something like pair of purely imaginary roots. Okay, pair of purely imaginary roots. Say, for example, plus or minus j omega. So pole zero plot you can draw. Say one root here and one root here. Plus sigma minus sigma. Okay, so this is plus j omega and this is minus j omega. What do you get? C of t. So if you have a system in which, let's say, the roots are located on either side of the imaginary axis, your response becomes sustained response. So whenever the system exhibits such type of response in which the amplitude and frequency, the amplitude keeps on wobbling between positive maxima and negative maxima, and the frequency remains the same, right? It oscillates at a constant frequency. If such is the system response, or if such is the pole zero plot, then your system is said to be marginally stable system. All right. Now that you got to know that, in order to get a marginal stability, when you equate the auxiliary equation, you should get roots of this kind. Because when you get roots of this kind, you will get the sustained response. Sustained response is nothing but a marginally stable response. Okay. So this is the second possibility to have the dominant roots. Okay. Third possibility. Third possibility. Third possibility is non-repeated roots. Non-repeated roots on imaginary axis. Okay, non-repeated roots on imaginary axis. In bracket you write complex conjugate. All right, complex conjugate with zero real part. Non-repeated roots on imaginary axis. That means to say they are purely complex with the zero real part. So what do you get the pole zero plot as? What do you get the pole zero plot as? Something like this kind you will get. Say, let's say this is j omega 1, this is minus j omega 1, and let's say this is j omega 2, and this is minus j omega 2. I'm very sure that everything I've discussed actually in the beginning of this stability chapter. So whenever you have a pole zero plot of this kind, your C of t basically takes the following shape. Okay, so it oscillates at, let's say, frequency omega 1. Your output is consisting of two parts. One oscillates with omega 1 and the other oscillates with omega 2. So probably I can use a red color. So omega 2. Okay, so this red stands for omega 2. Amplitude, I don't know. I mean, they will have different amplitudes, or probably they can even have the same amplitude. It depends. It depends. All right. So that is the second part, amplitude and the frequency. Of course, frequency is omega 1 and omega 2 because you can clearly make out that the vertical distance along y-axis is omega 1 and omega 2. So this vertical distance corresponds to frequency. Now, what do you call this type of system? Again, it's a marginally stable system. That's because the system is neither unstable or not stable. It keeps on, fluctuating between plus maximum and minus maximum. Okay, so it's a marginally stable system. So if you get the dominant roots of this kind, you can call it as marginally stable system. Okay. So quickly to recall, how many roots did we analyze? 3 roots, right? So out of 3 roots, we found that 2 roots can give us marginally stable condition, and 1 type of combination can give us unstable condition. Okay. Next up, we have the 4th type. Trust me, this is the last root nature which I'm going to discuss. All right, 4th type. 4th type is something like repeated roots on imaginary axis. Okay. Repeated roots on imaginary axis, and in bracket, just to clear it out, purely complex conjugate. All right, they are purely complex root, but conjugate here. Now, how do we understand the meaning of repeated roots on imaginary axis? Something like double roots, we say. Okay. So let's say you have a pair of roots in the positive j omega axis and pair of roots in the negative j omega axis. Let's say this is plus j omega, comma, plus j omega. Why? There are 2 roots. Similarly, minus j omega and minus j omega. Now, if this is your pole zero plot, then your time response, C of t, becomes something like this. You will get kind of exponentially growing oscillations, or something like, okay, this is the envelope, kind of rampish oscillations you get. Okay. And these oscillations, keeps on growing. Okay, of course, it starts from here. Okay. When you give a step excitation, what happens is that initially it jumps to 1, and after that, the catastrophic effect you will be able to see. That means to say, the amplitude keeps on growing. So this is unstable. Why unstable? It gives unbounded output. It gives unbounded output. There is no boundary for the output. You do not know what is the maximum value. Maximum value keeps on increasing with respect to time. All right. So just to wrap up, what we can say that when we encounter difficulty 2, the system stability is judged on the basis of the presence of dominant roots. So to find dominant roots, we have to solve the auxiliary equation. Once we solve the auxiliary equation, by knowing the root nature of dominant roots, one can judge on system stability, as in whether the system is marginally stable or unstable. So to judge the stability, we have to see the dominant root falls in which category, because there are 4 possibilities of dominant root nature. So 2 possibilities will give marginally stable system, and 2 possibilities will give you unstable system. Okay, so let's try to understand this dominant root nature with the help of a problem. Okay, so that's about the theoretical aspect of dominant roots. And this dominant root concept is very, very important when it comes to control systems lab. All right. So in Viva, you will be asked to explain what do you mean by dominant roots, or what do you mean by marginal stability. So marginal stability in terms of RH criteria, you can say that whenever in a RH table, when we encounter a row of zeros, then you can say that at that particular instant, the system tries to tell the designer that the system may experience marginal stability. When you get row of 0, you can say that the system may experience marginal stability. Okay, whether exactly it is marginally stable or unstable, that can be judged by finding out the roots of the auxiliary equation. Okay. So much I spoke, right? Fine. What do we have? Okay. All right. I would say this is a crazy problem. Okay. Fine. Take down. So for the system shown below, determine the stability. So what you have is the system's characteristic equation, f of s. So f of s is given as s to the power 6 plus 4 s to the power 5 plus 3 s to the power 4 . So the system shown below, determine the stability. I can say it is unstable directly. You don't have to apply Hurwitz criteria. Okay, that's because in Hurwitz criteria, I had mentioned one particular point. To apply Hurwitz criteria, you should have the positive coefficients. As you can see, this is minus 16, minus 64, and minus 48. So they are not positive coefficients, they are negative coefficients. If you have negative coefficients in your characteristic equation, you can directly say that the system is unstable. However, here there is second part also. Okay, that's the reason I want you to apply RH criteria. Okay, find the stability, and in part 2 you can write find the roots of this equation. Find the roots of this equation with positive real part, comma 0 real part, and negative real part. All right. So judging the stability is just a part of this particular question. In the second part, you are supposed to find how many roots are having positive real part, negative real parts, and the imaginary parts, purely imaginary parts. All right. So fine. So let's apply RH criteria. Okay. Let's start from highest power s, s to the power 6, s to the power 5, 4, 3, 2, 1, 0. So 1, 3, 1, 3, minus 64. Done. Then the missing terms. 4, minus 16, minus 40. Okay, so first 2 rows are constructed from the elements of the RH table. Okay, and yeah, you can start finding out the remaining elements. I think one I have missed. S cube term I have missed here. Right. 6, 5, 4. There is no 3 term here. S cube term is missing here. Okay, so you have to take it as 0 into S cube term. All right, so that was the mistake. So if you can see, it starts with the even power, right? So I am supposed to write down the coefficient of even powers of S. So 1 and 3. Okay, and then 16, because after 4 you have S to the power 2, which is S squared. So minus 16, and then minus 48. So this was the mistake. Okay. Somehow I felt uncomfortable while filling up the table. Okay, so that triggered me. Okay, now you can write down the missing term. So 4, okay, and then you have S to the power 3, that is 0. And S to the power 1, which is minus 64. And S to, okay, that's all. And then you can write down 0. All right. Fine. Now you fill up the table. Okay. You can 4 into 3 minus 0 divided by 4. So that is 3. Okay. Next you have 4 into 16. That is minus 64 minus of minus 64 divided by 4. So you will get it as 0. And this you will get it as 4 into minus 48 minus 0 divided by 4. So you will have minus 48 here. Okay. And then you find out the elements of S to the power 3 root. So 3 into 0, 0, minus 4 into 0, 0, divided by 3. So 0 by 3 basically, that's 0. And this becomes 3 into minus 64, minus of minus 48 into 4. Okay, so basically when you multiply, this also you will get it as 0. So as this. So there we have row of zeros. Row of zeros. Okay, you please cross-check your calculator when you multiply this and this. So 192 you'll get. So basically minus 192 minus of minus 192. So you'll get 0. So this is your row of zeros. So it is a special case. Special case. So once you get row of zeros, you cannot determine the elements of the remaining rows because everything gets multiplied. You can see here 0 into 0 minus 0 into 3 divided by 0. So infinity. Everything you will get abnormal entries. So you will have to come out of this particular case. So what you can do is, here you can write auxiliary equation. Okay. So what I will do, I will not write auxiliary equation here. I will write it here itself. So auxiliary equation A of S. Okay. So what is auxiliary equation? Auxiliary equation is an equation created from the coefficients of a row which is sitting above the row of 0. So what do we have here? So we have S to the power 3 row as row of 0, above which we have S to the power 4 row. So using S to the power 4 row, you are supposed to create auxiliary equation. So 3 into S to the power 4. Okay. Then there's a 0 coefficient, no point. So 0 into S square, that is 0, minus 48. Minus 48. So this is your auxiliary equation. Now, in place of zeros, you are supposed to substitute the coefficients of the differentiated equation, that is A dot of S. So A dot of S is nothing but dA of S by ds. So differentiate auxiliary equation with respect to S. So that gives 4 into 3, 12 S cube. That's all. 12 S cube plus 0 S. I can write just to maintain the dimension. So what do we have? In place of 0, okay, now you can substitute. I will write it in a different color. And then 0, and then 0. Okay, fine. Continue with the table. So 12 into 0 minus 3 into 0, that is 0, divided by 12 is 0. And then 12 into minus 48 minus 3 into 0 divided by 12. So basically you will get minus 48 here, and then you will get 0. So what is this? This is difficulty 1. Okay, this is special case 2. Difficulty of special case 1. What was your first special case? If first element in any row in a root table becomes 0, that particular element, that particular row will have at least one non-zero element. So this is your non-zero element. All right. So again, you cannot proceed with, because the remaining rows will have infinite values. So to come out of difficulty 1, what you can do is replace 0 with epsilon. Okay. When you replace only at the first element. So I'll write first element only. I hope this is visible. So instead of 0, what is that you are going to take? You are going to take a small positive integer epsilon. With respect to epsilon, you continue with the table. So what do you get? Epsilon into 0 minus 48 into 12 divided by epsilon. So you would get 576 divided by epsilon 0, 0, and the last element 576 by epsilon into minus 48 minus 0 divided by this. So you will get minus 48 here. So this is our root table. Now judge the stability. Is the system stable or unstable? Okay, because you have encountered row of zeros, the system cannot be stable, first of all. And is it unstable? Yes, it is unstable, because when we inspect the first column entry, we see that there are sign changes actually, right? How many sign change? Can anyone tell me? There is only one sign change. That's because positive 1, positive 4, positive 3, positive 12. It's a positive integer. And this is also a positive integer, right? Because 576 divided by epsilon will also be positive integer. So only at the s to the power 0 row, what has happened? The sign has changed from positive to negative. So you can write one sign change. Because there were sign changes in the first column, the system is unstable. And there was one sign change in the first column. You can say that there is one root is found in the positive, RHS of yes plane. So you can say that since there is one sign change, one root with positive real part is RP in RHS of yes plane. Okay. Because they have asked us to find how many roots with positive real part and negative real part and zero real part. Okay. So out of 6 root, you got to know about one root. That is one root with positive real part. So please mark this particular answer. So there is one root which is having positive real part because this particular root is found on RHS of the S plane. So obviously it should have positive real part. All right. Now we need to determine the roots which are having negative real part and zero real part. Okay. How do we determine? So the other roots can be found by equating the auxiliary equation. Okay. So let us write the auxiliary equation because as I said in the beginning, auxiliary equation is nothing but part of your main equation. And roots of the auxiliary equation are some of the roots of the main equation or the characteristic equation. Okay. So what was your auxiliary equation? Your auxiliary equation was 3s to the power 4 minus 48 is equal to 0. Okay. Or you can say that 3s to the power 4 is equal to 48. So since it's a fourth order equation, what we can do is put s square is equal to y. So put s square is equal to y. So obviously s to the power 4 becomes y square. So you can say 3y square is equal to 48 or y square is equal to 48 by 3. So 48 by 3 is I think 60. So y square is equal to 60. Okay, but what is y square? Y square is nothing but s to the power 4. So what you can write is y square is 60. So what you can write is y is equal to, okay, plus or minus 4. Right? One is positive root and one more is negative root. So plus 4 and minus 4. So the two roots. Okay. And okay. As a continuation, you can also say that y is s square. So basically, it is s square, right? So s square is plus 4. And you can also say that s square is also minus 4. Okay, because it's fourth order equation. And for simplicity, we have substituted s square with 1. Now, when you find yes, you will get yes 1 comma 2. First two roots. And when you find or solve for this yes, you will get 3 comma 4. Correct. Because y square is 60 and you have taken yeah, correct. You have substituted y is equal to s square. So what you get here, when you solve this, you will get plus or minus 2. And when you solve this, okay, s 3 comma 4 is equal to under root minus 1 into under root 4. So basically, yes 3 comma 4, you will get it as plus or minus j. And where is it? Yeah. So the four roots of this auxiliary equation is two real roots plus or minus 2 and two purely imaginary root plus or minus j2. Okay. So one root you have already found from root table, right? So one root was having positive real part. Positive real part. Okay. And from S3, 4, you can say that how many roots? Two roots. Do they have any positive real part? No real parts, right? So two roots having 0. Okay, let me write it in words. 0 real part. Okay. It's a sixth order equation. One root had positive real part, and two root had 0 real part. So roots, that is 6 minus 2 minus 1, that is 3. So the three remaining roots will have negative real part. So this is the question. So you can just write something like this. So two roots are having 0 real part, and one root was having positive real part, and the three roots are having negative real part. So three roots are found in LHS of the S plane. So this is the understanding of this particular problem. Okay. So I'm not writing where exactly is it real or complex conjugate. I don't know, because your RH criteria will not give you the exact location of the roots. It just tells you how many roots are present in RHS and LHS of the S plane. Okay. So this is the typical problem. Probably you can say the most complex problem which you can expect from the stability analysis. All right, fine. So I'll stop for I'll stop today's class, and probably in the next class let me solve a few more problems in which let us try to understand the relative stability concepts. All right. So if you have any doubts, you let me know. If you don't have doubt, probably you can drop off. Thank you so much.